Welcome to a webcast made by the Learning Enhancement team based in the Dean of Students office at the University of East Anglia. This webcast is part of the Steps into Calculus series and concerns finding stationary points. This guide describes how to use the first and the second derivatives of a function to help you locate and classify any stationary points the function may have. Introduction: Locating stationary points. The stationary points of a function are important in describing how that function works. Finding the stationary points of a function is a useful exercise, as you can use them in sketching the function or if you need to locate where the function changes direction. The three types of stationary points are a maximum, a minimum, a point of inflection. You can read the study guide Stationary Points for more information about the different types, sometimes called the nature, of stationary points. An important point made in that guide is that the stationary points are located where the gradient of a function is equal to 0. As the first derivative of a function describes its gradient, you can use the first derivative of the function to find out information about any stationary point the function may have. To find the location of any stationary points of a function you are looking at, use the following steps. Step 1. Differentiate the function to find dy by dx. Step 2. Set the derivative equal to 0 and solve the equation to find values for x. In other words, the x coordinates of any stationary points of your function are the solutions of the equation dy by dx equals 0. Step 3. Substitute these values for x back into your original function to find the corresponding y coordinates. Locating stationary points requires a good working use of differentiation. You should read the study guides Differentiating y equals ax to the n and Differentiating basic functions to help you with this. Example: find the location of the stationary points of the function y equals x cubed minus 3x plus 2. Step 1. To solve this question, you must find the first derivative of the function. This tells you about the gradient of the function. Using the power rule for differentiation, dy by dx equals 3x squared minus 3. Step 2. Set this result, 3x squared minus 3, equal to 0 and solve the quadratic equation for x. If you find this difficult, you can read the study guide Solving Quadratic Equations Using Factorization for advice. Here, 3x squared minus 3 equals 0. The left hand side has a factor of 3. So 3 multiplied by x squared minus 1 equals 0. The quadratic in the bracket is the difference of two squares, and so 3 multiplied by x minus 1 multiplied by x plus 1 equals 0, which gives solutions of x equals minus 1 and x equals 1. This means that you have two stationary points, one with an x coordinate of 1 and the other with an x coordinate of minus 1. Step 3. You can find the corresponding y coordinates by substituting x equals 1 and x equals minus 1 respectively back into the original function y equals x cubed minus 3x plus 2. At x equals 1, y equals 1 cubed minus 3 multiplied by 1 plus 2, which equals 0. So the y coordinate is 0, and this gives a stationary point at 1, 0. At x equals minus 1, y equals minus 1 cubed minus 3 multiplied by minus 1 plus 2, which equals 4. So the y coordinate is 4, and this gives a stationary point at minus 1, 4. So the function y equals x cubed minus 3x plus 2 has two stationary points at 1, 0 and minus 1, 4. Classifying stationary points. You can also use differentiation to classify the different types of stationary points. This requires the second derivative of the function, which gives information about the rate of change of the gradient. Mathematically, the second derivative is written as d2y over dx squared, which equals d by dx of dy by dx. Here, the left-hand side is the usual way you will see the second derivative written, and the right-hand side shows that it is the derivative of the first derivative. You may also see the second derivative written as y double prime. You can think of the second derivative as helping to reveal the shape of the graph of the function at some point. If the second derivative is positive, then the gradient of the graph is always increasing. Look at the curve on the right, which has a minimum. The gradient is always increasing as you go from left to right along the curve. But may not be so for the downhill section. However, you can think of the gradient getting less negative as you proceed along the downhill section, which means that the gradient is increasing. For example, a gradient of -2 is more than a gradient of -5. This means that if the second derivative is positive at a stationary point, that point is a minimum. If the second derivative is negative, then the gradient of the graph is always decreasing. Look at the curve on the right, which has a maximum. The gradient is always decreasing as you go from left to right along the curve. Again, this is obvious for positive uphill gradients, but may not be so for negative downhill gradients. You can think of the gradient getting more negative as you proceed along the downhill section, which means the gradient is decreasing. A gradient of -5 is less than a gradient of -2. This means that if the second derivative is negative at a stationary point, that point is a maximum. If the second derivative is 0, then the gradient of the graph is neither increasing nor decreasing. When the second derivative is 0, you cannot tell what type of stationary point you have. It could be a maximum, minimum, or point of inflection. In order to classify the stationary point, you need to do some further investigation. Pick two values of x, one either side of the stationary point, and calculate the two corresponding values of y. If both are more than the value of y at the stationary point, you have a minimum. If both are less than the value of y at the stationary point, you have a maximum. And if one is more and one is less, you have a point of inflection. See graphs below. You have a minimum if the y values of the points you choose are both greater than that of the stationary point. You have a maximum if the y values of the points you choose are both less than the stationary point. You have a rising point of inflection if the y values of the points you choose are below, before the stationary point, and above, after the stationary point. And you have a falling point of inflection if the y values of the points you choose are above, before the stationary point, and below, after the stationary point. Example: classify the stationary points of the function y equals x cubed minus 3x plus 2. Earlier in this guide you found that the stationary points of y equals x cubed minus 3x plus 2 are 1, 0 and minus 1, 4. To classify these points you need to find the second derivative. As the first derivative of y equals x cubed minus 3x plus 2 is 3x squared minus 3, differentiating again gives d2y over dx squared, the second derivative, equals 6x. you need to work out the value of the second derivative at each of the stationary points. For x equals 1, the value of the second derivative is 6 multiplied by 1, which equals 6, which is positive, and so 1, 0 is a local minimum point. For x equals minus 1, the value of the second derivative is 6 multiplied by minus 1, which is minus 6, which is negative, and so minus 1, 4 is a local maximum point. This is illustrated in the graph to the right. 1, 0 is a minimum point, but it is not the lowest point on the graph, and therefore it is a local minimum point. Minus 1, 4 is a maximum point, but it is not the highest point on the graph, and therefore it is a local maximum point. Example: find the location in nature of any stationary points of y equals 3x cubed minus 5. Step 1. Using the power rule for differentiation, dy by dx equals 9x squared. Step 2. Solving 9x squared equals 0 for x gives a single solution of x equals 0. Step 3. Substituting x equals 0 into y equals 3x cubed minus 5 gives a corresponding y coordinate of y equals minus 5, and so this function has a single stationary point at 0, minus 5. Step 4. The second derivative of the function is d2y over dx squared equals 18x. For x equals 0, the value of the second derivative is 0, which means further investigation is needed to classify the stationary point. As y equals 3x cubed minus 5 has a stationary point at 0, minus 5, you need to pick values of x either side of 0, for example, x equals minus 1 and x equals 1, and substitute them into y equals 3x cubed minus 5. This gives y equals minus 8 and y equals minus 2 respectively. As one value is larger and the other smaller than the value of y at the stationary point, the function y equals 3x cubed minus 5 has a rising point of inflection, as shown by the graph to the right. Further guidance and information. If you have any further questions about calculus, or would like to discuss any other aspects of mathematics, you can talk to your lecturer or personal advisor, or make an appointment to see a learning enhancement tutor in the Dean of Students office. Telephone 01603 592761. Email dos.help@uea.ac.uk, or visit our website at www.uea.ac.uk/dos/let. There are further resources on many other aspects of calculus, mathematics, statistics and science available from the Dean of Students office and on its website. These include questions to practice, model solutions and webcasts illustrating essential skills.